Hello, everyone. We come from Beijing Jiaotong University. We will present CEDA, our innovative system designed to tackle a crucial aspect of query optimization, cardinality estimation. I will introduce the 4 parts in order. Part 1: Introduction. What is cardinality estimation? Cardinality estimation is a fundamental and central issue in query optimization, aiming to predict the number of rows a query might return without actually executing the SQL query. For example, consider a relation R with n attributes and a query over R with a conjunctive of D predicates. The goal of cardinality estimation is to estimate the answer to this query. This is the image of traditional query optimizer architecture. From this we can see that cardinality estimator is a core component of the database query optimizer. With the application of machine learning in the DB community, researchers have begun to explore how to use machine learning to solve the problems of CE errors. Existing deep learning-based CE methods can be classified as data-driven and query-driven. However, both of them have disadvantages. Data-driven methods model the joint distribution over all attributes in the database. It leads to large model size and slow inference time. It do not support all kinds of queries. The query-driven methods learn regularities from historical workloads, which can be viewed as a supervised learning process. But it requires sufficiently large training workload, and obtain the workload is expensive. At the same time, query-driven methods suffer from workload drift. They tend to perform poorly when the feature distribution of the actual workload significantly differs from that of the training workload. If aiming to embed a deep learning-based cardinality estimation model into DBMS, the model should be lightweight, can achieve accurate CE results by fast inference and training. We propose an attention-based cardinality estimator incorporating histogram information. Under workload drift, the model may have unpredictably poor performance. Retraining or fine-tuning requires cardinality labels, and obtaining them from DBMS is expensive. So we adopt the domain adaptation strategy to solve it. In the part 2, I will introduce our system overview to you. This figure shows us the architecture of CEDA. It is composed of 2 main components, web service and server. An end-to-end cardinality estimation pipeline is supported by 3 modules: data preparation module, attention-based cardinality estimator module, and domain adaptation module. Data preparation module is responsible for collecting and processing metadata and query logs to generate training data for the attention-based cardinality estimator module. Attention-based cardinality estimator module can produce accurate estimation results by incorporating histogram information in the database. Domain adaptation module can use domain adaptation strategy to address the issue of workload drift. Next, let me introduce you to the core techniques. As shown in the figure, DA for attention-based cardinality estimator contains 3 key components: feature extractor, cardinality predictor, and domain classifier. Feature extractor is used to extract features and learn representations for SQL queries, which consists of MLP and attention mechanism. To mitigate the impact of data skewness on training and improve estimation accuracy for predicates never seen before, histogram information is introduced. We obtain the vector representation of the predicate by concatenating the vector of triple column, operator, value and the vector of histogram to help the model better understand the data distribution. Cardinality predictor is a regression predictor composed of 2 fully connected layers. It takes SQL feature vector X from feature extractor as input and predicts cardinality values. Domain classifier takes the SQL feature vector X extracted from F as input and determines whether X belongs to the source or target domain. The output of domain classifier can be used to compute the adaptation loss and adjust the parameters of F for domain adaptation purposes. We employ adversarial-based training to train the model, using only labeled data from the source domain to train feature extractor and cardinality predictor. During the training process, we use the Q-error loss function to optimize feature extractor and cardinality predictor. Feature extractor and domain classifier are trained using mixed data from the source and target domain to enable feature extractor to learn domain invariant feature representations. Use AGRL to confuse domain labels as much as possible, making it difficult for domain classifier to differentiate between the source and target domain. Finally, the loss function for the overall model in the adversarial training is expressed as loss CP minus loss D. Finally, let me tell you how to use our system CEDA. Hello, welcome to our system CEDA. In this demonstration, we will demonstrate how to easily use the CEDA platform for an end-to-end cardinality estimation. The first step, we connect to the database. We see the details of each table in the database. We can also click the fan-shaped part corresponding to the data table to view the specific information of its columns. The second step, workload generation. In the Basic Settings section, to avoid an explosion in the number of predicate and join combinations during SQL generation, we need to input the number of SQL statements, the maximum number of joins, and the maximum number of predicates. In the More Settings section, customized services are also provided for different user requirements under different business scenarios by selecting table name and column name. If the user does not select anything, the workload generated will satisfy the database distribution based on its metadata. Then we click the Generate button. The generated workload is displayed in the Generated Workload list in real time. Since the generated SQL statements should be labeled with true cardinalities obtained by DBMS, it takes a little more time here. In order to save time, we skip the process of generating each SQL statement. When the generating progress reaches 100%, the workload has been generated. Then we can click the Export button to export the generated workload file. The third step, let's train our attention-based cardinality estimator. We can click the Load Train Data button to import the training data. In addition to importing the workload generated in the previous step, we can also import our own workload. Then we set the 4 hyperparameters. It's here, we can decide whether to add materialized samples and histogram information to the training data by checking the checkbox. Then we click the Run button, and the attention-based cardinality estimator starts training. Training logs and progress will also be displayed in real time. In order to save time, we have trained our model in advance with the generated workload. Now, we can use the trained model to estimate the cardinality of the SQL statement. It's here, we can input an SQL statement with a multi-table join in the text box and click the Execute button. Then we view the estimated results of various methods and the comparison of the inference time in the results section below. From the two figures, we can see that our method beats the traditional database and the SOTA method MSCN dealing with multi-table join problems. Our method is more accurate and can compete with traditional database in terms of inference time. Furthermore, we can also import a batch of queries. For example, now we import the job light workload and choose how the Q-error is presented. We can select Line to display Q-error in a line chart or choose Boxplot to show the overall distribution of Q-error in a boxplot. It can be clearly seen in both figures that our method provides the most accurate cardinality estimation for multi-table joins. As business scenarios of applications continue to evolve, the workload of databases also undergoes changes. When the feature distributions of the training and real-world workload differ significantly, the model trained may often perform poorly on the real-world workload. For example, we import labeled training workload in the source domain and in labeled real-world workload in the target domain. By clicking the Run button, we can observe that the feature distributions of the source and target domains differ significantly before domain adaptation. Therefore, we can see in the line chart that the Q error before DA is very high. After we click the Workload DA button, the system will use the domain adaptation strategy to train the cardinality estimation model. When the training is completed, we can clearly see that the model aligns the feature distribution of the source domain and the target domain. After DA, the Q error has been significantly reduced. It is worth noting that domain adaptation not only avoids the expensive cost of labeling real-world workloads but also improves the generalization ability of the cardinality estimation model. This is end of our demonstration. Thanks for watching. That's all. Thank you.